السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم. إن شاء الله اليوم مكملين معاكم بسكشن 18.4 or sections اللي شرحناهم together. Okay. وهذا هيكون آخر example بهذا السكشن. So خلينا في البداية نقرأ السؤال. So the wheel weighs 20 kilogram. Here is the wheel. Okay. And its weight is 20 kilogram. This is M. Okay. And has a radius of gyration K with subscript G for the centroid, 0.18 meter, about its mass center G. If it is subjected to a clockwise couple moment, this is the moment, and rolls from rest, this is very important, we'll come back to this word, without slipping, so there is no slip. Determine its angular velocity after its center moves 0.15 meter. So we need to find omega. So omega is unknown. But when this omega is needed after its move certain distance. So this is rest, and then it moves to the right. This movement was 0.15 meter, the displacement. The spring has a stiffness 160 Newton per meter, and it's initially unstretched when the couple moment is applied. Okay, so it starts from rest. Spring was unstretched, then after the center moves distance 0.15, it becomes stretched. Now we need to find omega. Okay. Now, how to solve this problem? We'll benefit from the principle of energy and work. Let us move to the solving board. Okay, and let me first write the given information. So we have mass equal to 20 kilogram. Let me use black color. And also we have radius of gyration kg. So this gives us 0.18. And let us calculate the mass moment of inertia about G as well, which is equal to mass multiplied by kg squared, and this is equal to 20 multiplied by 0.18 squared. So the answer is, let me use my calculator, 0.18 squared multiplied by 20. So this is 0.648 kilogram meters squared. Okay, what else? We have a couple moment of 22, and we have a displacement of, so here is the displacement, s equal to 0.15. This happens at state 2. State 1, it was 0. Let me draw let me first write the equation. So the equation for the principle of energy and work is equal to T1 plus summation of work between 1 and up to 2 equal to T2. So what do we have? We have a wheel. Okay. It starts from rest, so nothing happens. And then at state 2, it moves a distance. So here is the initial position. This is state 1. And here is the new state. Okay. So this is G, the new location of G. And this distance is 0.15. Okay. And I name it, or I call it as. Okay. You know what? Let me change the name so you're not confused with the stretch of this spring. So I will name it L1 and I will name it L2. Okay, this is much better because this is the movement of the centroid. Okay, because in the problem statement it's mentioned that the center G moves 0.15. So here is center G, and here is the point where the spring is attached. Okay, at point A. So let me go back to the question. Finish solving board, sorry. So in state 2, what do we have? Here is the wheel. We have couple moment applied, which is 22 Newton meter. What else? What do we have? I need to draw the free body diagram, okay, in order to decide which of the forces and moments do work. Okay, so here we have spring force, which is opposite to direction of motion. What is the direction of motion? In this direction. Okay, what else? What do we have? We have weight on the centroid. So this is W. What else? We have reaction from the ground, normal force, and as well as we have friction force. The friction force either will be in this direction, okay, or it will be in this direction. Which one is correct? This direction or this direction? It's better to discuss this issue in the coming live session, okay? So please remind me to explain it to you. Okay, so the correct answer is in this direction. Okay, so now the question is, which one of these forces will do work? Okay, what do you think? Is normal, does the normal do work? The answer is no. Why? Because the displacement in the horizontal plane and this force in the vertical. What about the friction force? Is this force, will this force do work? The answer is no. Why? Because we have rotation without slipping. Okay, if it is without slipping, then there is no work due to this force. What about moment? Moment will do work. How about spring force? Spring force will do work because spring force in the same direction of displacement. Okay. Let's go and start substituting in the equation. Okay, we have T1 summation 4 plus T2. Okay, T1 or T in general will equal to half mvg squared plus half ig omega squared. So in state 1, the wheel is at rest. Okay, there is no stretching even. There is nothing. Okay, so since it is at rest, velocity is equal to 0 and omega equal to 0. So as a result, T1 will go to 0. Okay, but in state 2, there is certain velocity, there is certain displacement. Okay, so there is value for T2. Okay, so let me substitute T2. So T2 is equal to half mvg squared plus half ig omega squared. Okay, and instead of vg I write, so T2, either I can substitute this equation, or I can go directly and say half I with respect to instantaneous center of zero velocity multiplied by omega squared. Why IC? Because this is a rotation or general plane motion for a wheel that rolls without slip. Okay, so there is IC, instantaneous center. Okay, let me stick to the first format. I'll erase this one and I will substitute. This is equal to half m. Instead of Vg, I write R multiplied by omega squared plus half Ig omega squared. Let me take half and omega as a common factor, okay, and we'll end up with Ig plus m Rg. Okay, so this is half omega squared. Okay, and even this R is squared. Sorry for this mistake. Okay, because V is squared. Okay, then if I substitute R omega, then R will be squared and omega will be squared. Okay, so if you remember the parallel axis theorem, this equation in the brackets will lead us to the same result. This is represent I with respect to IC. Why? Because this R is the relative position vector Rg with respect to IC. Okay, so everything here is known except omega. So this is equal, this is T2 equal half omega squared. Instead of Ig, I think we managed to calculate this value at the beginning, and it was 0.648. Point 648 plus mass of the wheel, which is 20, and radius of this wheel, or the distance between centroid and the IC, is same as the radius, which is point multiplied by 0.24 squared. Okay, and if I use my calculator, 0.24 square multiplied by 20 plus 0.648 multiplied by half. So this is 0.9 omega squared. I will name this equation 2, and the previous equation I will name it 1 in the first sheet. This equation I will name it 1. Okay. Now we could find this equal to 0. This one is ready. Now we end up with summation of work. So in order to find summation of work, we start with classifying which force will do the work. So summation of work from 1 to 2 is due to work due to spring force plus work due to moment only. I'll calculate each one separately. So work due to force of the spring, which is equal, always we said it's minus, so minus half multiplied by K S2 minus S1 squared. In the statement of the problem, it's mentioned that this spring was initially unstretched. Remember? Let me go back to the statement or problem statement. So it is initially, here it's mentioned, unstretched. Okay, so I'll substitute S1 equal to 0. Okay. So, and the stiffness of this spring is given in the figure of the problem, which is 160 multiplied by S1 is unknown, but S2 is unknown, but S1 is 0. So this one go to 0. Now we end up with S2. How to calculate S2? In order to calculate S2, here is the initial state. Okay, here is G. Okay, and here is point A. Okay, okay, and here is the IC point. Okay, and here is the wheel. Okay, but I will not draw the wheel. Okay, so the problem tells us that this is location 1. Then this center moves distance of, this is state 2, and this distance is 0.15. Okay. Now where is the new location of A? The new location of A will be at certain location here after certain time. Okay. So this is the initial location, and here is the final location. So yeah, this distance is unknown, and we can call it S2, the new stretching. Okay, so this theta is unknown as well as S2. Okay, so this theta is unknown and S2 is unknown. How to find them? We have this triangle, this distance is known, which is the radius of this wheel, which is 0.24. And again, this distance is known, 0.24, the radius. So the whole distance is equal to 0.48. Okay. And this distance is known, 0.15. I'll write it here. So in order to find S2, we need to find first of all theta. So here, this distance 0.15, which represents the movement of this point S, and this is equal R multiplied by theta. Why? Because here is the disk, okay, and here is the point, here is G. Imagine that this IC is fixed point, so this point G will rotate like this distance, okay, will do circular motion. So here is the new location, okay, so this is S, which I represented as a straight motion, and here is theta, and here is R. So the equation that gathered them together, so theta equal S divided by R, so this is equal 0.15 divided by 0.24. So this is equal 0.6. This is equal 0.6 rad. This is theta. Now, in order to find the stretching in the spring, okay, so I name this theta 2 because theta 1 is equal to 0, and we benefit from this in calculating work due to moment equal to 0, and theta 2 equal to 0.6 rad. Okay. Okay. Now, in order to find stretching, where is stretching? Which is the second arc, this one. What we'll do? So S2, which is equal to theta multiplied by r, or multiplied by not r, the whole distance, which is diameter. Okay, so this is equal to 0.6 multiplied by 0.48, 0.6 multiplied by 0.48, and the answer is 0.288 meter. So now I can calculate work due to spring. Okay, I think it's in the previous slide. So U due to spring is equal to minus half 160 multiplied by 0.288 squared minus 0. Okay, so this is equal. So 0.288 squared multiplied by 160 divided by 2, this is minus 6.635 Newton. Now, the work due to moment is equal to, so U due to moment equal to moment multiplied by theta 2 minus theta 1. Okay, and this sign is positive. Why? Because the direction of moment and theta in the same sense. So here we have 22 multiplied by 0.6, and this gives us, let me calculate it, 22. This is 13.2. And in order to find the total work, then U total equal to U from moment plus work from spring. So this is 13.2, okay, 0.2 minus, I think it was 6. Yeah, it was minus 6.635. Minus 6.635, and the result is 6.565 joule. Okay, so this is U, the summation of the work. I named this equation as. Now we'll substitute equation 3 and 2. Substitute equation 3 and 2 in 1. So what do we have? 0. This is kinetic energy 1 plus summation of work equal to 6.565, and kinetic energy 2 was equal to 0.9 omega squared, then omega equal to under root square 6.565 divided by 0.9, and this gives us, let me use my calculator, 2.7 rad, sorry, pairs. Okay, so if I go back to the PowerPoint, yes, the answer is 2.7 rad per second. Okay, So that's it for this section. Now let's move to a new section. So the remaining section is 18.5, which talks about conservation of energy. Okay, so conservation of energy means that the energy is conserved. The energy will not be lost to the surrounding, or the energy will be reversible. So the objective is to apply the theorem. Let me hide this bar. We need to apply the theorem of conservation of energy to solve the kinetic problems. The application, this is very famous application in the United States of America. So here what do we have? We have a garage, okay, and this is the door of this garage. Usually they use torsional springs, okay, as you can see here. This torsional springs located at the top of the garage door, and it's wind up, okay, squeezed as the door is lowered. So whenever the door is going down, this springs become compressed or squeezed or wind up as the door is lowered. When the door is raised, the potential energy stored in the spring. So whenever the door is lowered, the spring store potential energy, or we'll call it in the coming slide elastic potential energy. Okay, and the term potential energy will give it a name of V. Okay, so this is V, and we'll have two types of potential energy: V elastic, okay, due to spring, and we have V due to gravitation. Okay, so whenever the door is lowered, then those springs will store elastic potential energy. Okay, when the door is raised, okay, when the door is raised, عندي حيصير تحول في الطاقة energy transfer from one shape to another. So the potential energy stored in the spring is then transferred into gravitational potential energy. هذا الباب كله بيرتفع للأعلى، okay. والطاقة بتتحول من elastic to gravitational اللي هو وزن الباب، okay, into gravitational potential energy, the door's weight, thereby making it easy to open. هلا لما يوصل لأعلى نقطة والباب يوصل كله للأعلى، ونيجي بدنا lower down, okay, the potential energy or the gravitational potential energy start to convert again into elastic, and etc. Okay, so here we can say that the energy is conserved. Okay, so energy changed its form from one shape to another. Okay, but it not will be lost to the surrounding. When we can say that we have conservative force or non-conservative force, and what is the meaning of potential energy? So conservative force, we can name it as this when it's independent of the path. Okay. So examples: gravitational force or weight, and elastic force, spring. So this is very famous example: the elastic force and the gravitational force due to weight. Those depends on the state, not on the path. Okay, these forces are depending only on the initial and the final position. So it depends on the states of the body. It does not depend on the path. While the non-conservative force is the frictional force. Frictional force is non-conservative. Then it depends on the path. Okay, so it depends on the path. Like for example, wheels rolling without slipping or rolling with slipping. Okay, so it depends on the path. So this type of force is non-conservative. Why? Because this is non-conservative, because the work is dissipated as a heat. So we have work due to non-conservative force. Okay, and the most famous work is work due to friction force. Okay, this force is lost, or this work is lost to the surrounding. Potential energy, whenever we said energy or potential energy, it means the ability to do work or the capacity to do work. Energy comes in form of kinetic, or it may come in the form of potential. Kinetic, we saw it before, and we give it symbol T. Potential energy will give it symbol V. Okay, potential energy and its symbol is V. At any point in the time or state of position, we can say that the body has some of potential energy. Some, that means we have types, okay, of potential energy. The most famous types of potential energy is the gravitational and the elastic potential energy. Let us discuss them one by one. First, gravitational potential energy. Okay, so its equation is equal to weight multiplied by displacement, and both of them must be parallel to each other. Okay, so متى بنعوضها positive متى بنعوضها negative? When the sign of elastic potential energy is positive and when it is negative. For example, if this is our reference, okay, this is our reference, and this rigid body moves vertical distance from this location to this location, okay, then whenever this rigid body in top of this reference and the displacement is in the top of this reference, we'll substitute it positive side. Okay? If the displacement of the rigid body happens below this datum, then directly we'll substitute it minus. Okay? So this is positive y because the displacement happened on top of the reference, and this displacement or this potential or gravitational potential energy is negative because the displacement of this rigid body happens below this reference. Okay, this is why. So whenever we are in top of the datum or above the datum, then we'll substitute y as a minus, as a positive, and whenever we are below the datum, we'll substitute y as negative. Elastic potential energy. Okay, so if you stretched this springs and you move your rigid body a distance s, then the elastic force will always be positive. Why? Because this energy will store potential or elastic potential energy. Okay? So notice that elastic potential energy is always positive. Okay? So because it is stored energy. Even this is stretching. If it is compression, again it will be positive. Why? Because it stored energy. Okay? It gain energy. Conservation of mechanical energy. This is another rule that we'll use it. Okay? So عادة الأسئلة بهذا الشابتر بيجي بيحكي لك use مثلا البرنسبل اللي تعلمناها في section 18.4 use the principle of energy and work، أو بيجي بيحكي لك use conservation of mechanical energy اللي هي البرنسبل اللي احنا نتعلمها في هذا السكشن. Okay. So the principle of work and energy for a rigid body. So this is the principle. Okay. نحكي قاعدين عن البرنسبل شفناها ب 18.5 but we'll add potential energy. Okay. So here is the principle of work and energy. Okay. But because we are talking about conservative, then this term will go to 0. Okay. So if we are talking about conservative, so here summation of u from 1 to 2 is non-conservative due to non-conservative force. Represent the work of non-conservative force, such as a friction. So this term will vanish, okay, will go to 0, and we'll end up with this format. T1 kinetic at state 1 plus potential at state 1. Okay, never mind whether this potential is due to V1 gravitational or V1 elastic. Okay, equal to kinetic energy state 2. It could be translation, rotation, or general plane motion plus potential energy state 2. Okay, this form of equation we call it as conservation of mechanical energy. So إذا إجا السؤال حكى لك use conservation of mechanical energy to solve this problem, you must write down this equation. Okay. If the question told you to solve using principle of energy and work, you must use equation in section 18.4. Okay. Let's see this problem. Example 18.5.1. In this problem, the 10 kilogram rod AB, so here is the AB, and this rod is 10 kilogram, its weight, its mass, shown in the figure is confined, حركته محددة, so that its end moves in horizontal, this end move in horizontal in this channel, okay, with the slider, and this point confined to move in vertical in this channel with the slider. Okay, so it's confined so that its end moves in horizontal and vertical slots. Okay, بهذول channels or slots. The spring has a stiffness. The spring has a stiffness of 800 and is unstretched when theta equal to 0. So when theta equal to 0, that means this spring or this bar is located completely horizontally, and the spring is unstretched. So S1, where is it? So S1 equal to 0, or I will not name S1, I will wait until the end. Okay, I will call S equal to 0 when theta equal to 0. I will name it like this, and I will do it. Later on, I'll decide whether it's 1 or state 2. Determine the angular velocity of AB, so we need to find omega AB when theta equal to 0. This is unknown. If the rod is released from rest, this is V1 equal to 0. When theta is equal to 30, so this is theta 1. Okay, that means we'll start from this angle. This is state 1. And then we'll release it. Where will go? It will rotate like this until it reach state 2. This is state 2. Okay. So as a result, this is S2, theta 2. Okay, and this one is theta 1, V1. Neglect the mass of the slider blocks. Okay, we'll neglect the mass of block B and block A. Let's move to the solving board. Okay, and I'll open a new solving sheet. And I'll start with writing the given information. Okay, we have mass of the rod AB equal to 10 kilogram. Okay. طبعا at the end of the example of the statement of the problem, we can come and say use the conservation of mechanical equation. Okay, so this equation. Use the conservation of mechanical energy equation. So if I add this statement, that means you must use 18.5. Otherwise, you can go and use equation in the 18.4. Okay, or you can benefit from any other topics in this material. You can go back to chapter 22, chapter 17, and solve this problem. Okay, so yeah, let me go and continue writing the given information. But make sure whenever we write the way that you must solve, and it will be the most easiest way, most easiest scenario. Okay, so state 1, and here we have state 2. In state 1, what do we have? We have this spring, okay, and here is the rod location. This is point A, and here we have point B, okay, and it starts from rest. It means that V1, because it's mentioned that it starts from rest, then V1 equal to 0, and theta 1 equal to 30. Okay, where is theta? This is theta. Theta 1. Okay, now how about S1? How about S1? Let's see. Before going back to the PowerPoint figure, let me continue with the state 2. So here is the spring. Okay, and here is the new location of the rod. This is A and this is B. So theta 2 is equal to 0, while V2 is unknown. Okay, and S2 is equal to 0. This is given in the problem statement. Okay, now in order to find out S1, this value here, let me go back to the PowerPoint presentation. So here it is. Let me erase everything. So at this location, let us assume that this is 30. Okay, and this distance, or at this location, if the rod is at this location, will have no stretching. That means this distance represent the stretching of the spring at state 1. So if the rod at this state, this distance represent what? S1. How to calculate S1? We have theta 30. Okay, this is given, and we have the length of this rod, which is 0.4. So how we can calculate S1? It is sine theta, which is S1 divided by 0.4. So let's go back to the solving board. So S1 equal to, let me go a bit lower. So we say that sine theta equal to S1 divided by 0.4, or S1 equal to 0.4 multiplied by sine 30. As a result, is equal to 0.4 sine 30 using calculator. And this is equal point. Okay. Now, if I want to use the conservation of mechanical energy equation, then this is V1 plus T1 equal to V2 plus V or T2. Let me start solving one by one. So T1 equal to half m Vg squared plus half Ig omega squared. But it's mentioned that, and we substitute here, that it starts from rest. Remember? So if it is started from rest, then T1 will go to 0. Because this term is 0, no omega, and there is no velocity. So this term will go to 0. Okay? Now, I'll start with the easiest terms first. Okay, then we'll go to the difficult one. How about V2? V2. V2 is equal to V2 elastic plus V2 gravitational. Okay? In location 2, let me go to a new page. In location 2, here is the spring. And here is the new location, state 2. Okay? This is point B. And this is point A. Now, and let me also draw the first location. This was the first location. Okay, I'll choose the reference. What do you think? Which is the best? I think the best is to choose our reference in here. This is our reference. Okay, so V2 elastic, which is equal to half K S2 squared. But we mentioned that this spring is unstretched when theta equal to 0. So this term will go to 0. Now, V2 gravitational, which is equal to y multiplied by weight, displacement multiplied by y. Do we have any displacement at state 2 between the reference and the bar? No, they are coincident on each other. Okay, متطابقين. So here is the g, here is weight, and here is the centroid. So is there any displacement between the reference and the bar? No. So this value again will go to 0. So if I go back to the first sheet, so V2 again is equal to 0. So we end up with V1 and T1. V1 and T2. So we end up with V1 equal to T2. So V1, again, it's due to elastic 1 and it's due to VG1. V elastic 1, which is half K S1 squared, and Vg1, which is due to y multiplied by W. So this is always positive. Half. The spring stiffness is 800. Okay, multiplied by S1. I think we calculate S1. Okay, and it was, let us read that together. 0.2. Okay, was 0.2. So let me go back again. So I'll substitute here 0.2 squared, and this is equal to, so 400 multiplied by 0.2 squared, which is 16 joule. Okay, so this is the elastic potential energy state 1. This is, and the gravitational potential energy weight multiplied by y. But whether this value positive or negative, what do you think? Is this bar at this state below reference or in the top of the reference? And how about the distance? Let me change the picture. So here is the centroid, okay, and this is the distance, vertical distance between the centroid at state 1 and the reference. Okay, so this is y, and once we are in the below the reference, then we must substitute minus sign. But this distance is unknown. Okay, we have this theta equal to 30, and this distance equal from the problem statement 0.2. Okay, then we can calculate y. So y equal to 0.2 sine 30, which is equal to 0.1. Okay. So we must substitute it minus. So this is minus sign here. So minus. We have 10 kilogram multiplied by 981 multiplied by 0.1. So this is equal to minus 9.81 joule. This is Vg. Okay. Let me name this equation as 1, this equation as 2, this equation as 3. Okay. Or do you know what? Let me calculate V1, which is the summation of V elastic 1 and V gravitational. So V1 equal to V gravitational 1 plus V elastic 1, and this is equal to 16 minus, so this is 6.19 joule, and then I will name this equation as equation 2. Okay? Now, I think I should go back to solving board. Now, how about T2? Let me go to new page. T2 is equal to half mvg2 squared plus half ig multiplied by omega squared. Okay. Now, instead of Vg, I will write, so I will take half as a common factor. Mass multiplied by r squared omega squared Ig omega squared. But this velocity, centroid velocity, what we can substitute this centroid? Let me go back to the PowerPoint and let me erase everything. So whenever the bar in this location, uh, this is the centroid, and we need to find out the magnitude of this centroid. But first imagine that this cylinder is sliding to this direction, okay, up to here. So here is the new location. As in the same point, whenever this slider go in this direction, this slider will go in this direction, correct? So whenever the slider B reach this location, this one, the slider A will reach the maximum or the farthest point. Okay, توصل لأبعد نقطة وبعدها مش رايح يتحرك، وكأنه لحظيا النقطة A لما وصل على الهوريزونتال arrangement وكأنه ثبت، وكأنه سرعته ايش؟ زيرو. So velocity A وكأنها زيرو. ليه؟ لأنها وصلت لأبعد نقطة. طبعا هذه أبعد نقطة، وبعدها لما يعمل stretching spring ينزل هذا للأسفل، بلش هذا slider closer become closer to the spring. okay بيتحرك في هذا الاتجاه. طيب بما ان هذه النقطة حتكون لما يكون بالهوريزونتال ارينجمنت هذه بتكون ابعد نقطة وبتكون زيرو، كانوا لحظيا بتوقف. النقطة G with respect to A اللي هي نقطة الزيرو حتكون سرعتها، لأن هذا الرد بيتحرك بهذا الاتجاه، بالتالي هذه النقطة حتكون اتجاه سرعتها للأعلى. This is VG. So VG شو بتساوي؟ أوميجا multiplied by أوميجا للرد multiplied by relative position vector بين G و A. G with respect to instantaneous center of zero velocity اللي هي نقطة A لحظيا زيرو. It is not instantaneous, it is zero velocity. Okay. كأن هذه نقطة بتثبت. So let me go back to the solving board and write that this is RG. Now I can take half omega squared common factor and we end up with IG plus MRG squared. هذه المعادلة كأنها parallel axis theorem with respect to IA. Now we have a rod. If we go back to the uniform shapes, you will find out that the IG is equal 1 over 12 m mass of the rod, which is 10, multiplied by the length of this rod, which is 0.4 squared, okay, multiplied or plus 10 multiplied by 0.2 squared. Okay, and this is equal, use my calculator, multiplied by 0.4 plus m by 0.2 squared, divide by 2. So this is equal 0.2 omega squared. This is T2. This is equation 3. Now substitute 2 and 3 in 1. Substitute 2 and 3 in 1. Then we'll obtain that T2 is equal to 0.266 omega squared, and V1, let me check the value. V1, let's go up. Okay. V1 it was 6.19. So omega equal under root square 6.19 divided by 0.266, and this is equal to 4.82 right there. Okay, so this is the answer of this problem. Omega equal to 4.82 rad per second. If we check with the slide, yeah, it is correct, 4.82 to rad per second, and it's counterclockwise because this rod rotates in this direction. Okay, so this is one problem. The other problem we'll solve it together in the coming slide, in the coming lecture. So this is the second problem. We'll solve it next time. Once we solve it, we'll move to new chapter and the last chapter 19. Okay, until then, stay safe and see you soon.